After watching the sex inheritance video, let's practice a couple of sex linkage problems. Many genetics problems will ask you to get a lot of information from reading a paragraph. So let's start with this paragraph. Rickets is a disorder causing soft, weak bones, often resulting in bow-leggedness. There are two types of rickets. One is environmentally determined due to a lack of vitamin D, which comes from exposure to the sun. And then there's also a genetic disorder, also called vitamin D resistant rickets. And that's due to a mutation on the X chromosome. So we have a man with vitamin D resistant rickets who has 4 children. His children's mother does not have rickets, but she is a carrier for the disease. So let's draw out our genotypes here. We know that this is an X chromosome mutation, and since we're talking about humans, we can write down the genotypes of the parents. All right, we've got the female and the male. We know that the man has vitamin D resistant rickets, so I'm going to put a little d on his X chromosome. The wife does not have rickets, but she is a carrier. That indicates she is heterozygous for the disease. Carrier means heterozygous for the disease. So how many of their children do we predict will also have rickets? Let's draw the Punnett square. I'll use the male here on top of the Punnett square and then the female on the side. Based on this Punnett square, it looks like 50% of their children will have rickets. And this answer is the same for both boys and girls. Because girls have 2 copies of the X chromosome, they will receive a little d allele from their father no matter what, but only 50% of the girls will also receive a little d allele from their mother, whereas 50% of the boys will receive a little d allele from their mother, and that's all that they need to manifest vitamin D resistant rickets. All right, another paragraph of information. A woman who is a carrier for X-linked hemophilia. Let's draw in her genotype right away. She is a carrier for X-linked hemophilia. She marries a man who does not have hemophilia. So there is the spouse's genotype. They have a daughter named Angela who does not have the disease. If Angela doesn't have the disease, she can have 2 different genotypes. She could be X plus X plus, or she could be X plus XH, depending on which X she gets from her mom. Angela marries George, who does not have hemophilia, so we know his genotype must be X plus Y. Angela and George have a son named Robbie. Robbie gets an X and a Y. What's the chance that Robbie will have hemophilia? In order to solve this problem, we need to rely on the multiplicative rule of probability. We want to calculate the probability of Angela being a carrier for hemophilia and the probability of Robbie having hemophilia. Because remember, Robbie could be XH or X plus. Okay, so for multiplicative probabilities, we need to know the probability of this occurring and the probability of that occurring, and then multiply them together. So the 2 possible genotypes that Angela could end up with are equally likely. That means we have a 1/2 probability that Angela will be a carrier. And then we have 2 possible genotypes for Robbie depending on his mom's phenotype. And there's a 50% chance that he will have hemophilia. That's 1/2. So 1/2 times 1/2 gives us a 1/4 probability that Robbie will have hemophilia. In this problem, we know that colorblindness is an X-linked recessive trait. A colorblind female has children. What do we know about her sons? Well, first, what do we know about her genotype? She's female, so she has 2 X chromosomes. And if she's colorblind, that means she carries the colorblind recessive allele on both copies of her X chromosomes. So, will half or all of her sons be colorblind? If we draw a Punnett square, regardless of what the dad's genotype is, she's going to pass on a colorblind X to all of her sons. We know then that all of the sons will be colorblind because they will all receive a colorblind allele from the mom. So not half, not normal vision, they will be colorblind. This won't affect her ability to have a son. And as far as sons' phenotypes are concerned, we don't need to know the father's genotype because for a son, a father is only contributing the Y chromosome. And the Y chromosome doesn't carry the colorblindness gene. If the question asked about the daughter, then we would need to know the genotype of the father's X. The mom only has colorblindness alleles to pass on to her daughter, so we know that they will all at least be carriers for the allele. But if the dad is wild type for colorblindness, he might produce a daughter who was just a carrier, or if the dad was mutant for colorblindness allele, he could produce a daughter that was also colorblind. But for sons, the father contributes a Y and the mother contributes her colorblindness alleles to all of the sons.